So let me introduce our next presenter. The presentation is about system-level test needs, requirements, and equipment. The presenter is Karr from Texas Instruments. He's a reliability applications engineer and senior member of the technical staff in the test technology group at Texas Instruments. He has held various engineering and management roles during his 40-year tenure at Texas Instruments, including product and test engineer, engineering section manager, product branch manager, test platform manager, and burn-in platform manager. He's co-inventor on several burn-in related patents, an author and co-author on multiple burn-in related technical papers, and is a frequent trainer on reliability related topics. He's a BSEE graduate from the University of Illinois in Champaign-Urbana. So, Rich, please start your presentation. Thank you.
All right. Thank you, Mark. Hello, everyone, and welcome to today's session. My name is Rich Karr, and as Mark says, my presentation explores my journey investigating system-level test needs, requirements, and equipment. Just a quick note that during this presentation, I'm going to frequently interchange system-level tests with the synonym SLT, or acronym SLT. So be wary of that. And I've also added a list of acronym definitions at the end of the slide set. As you know, we're pretty strong on acronyms in our industry. So in this presentation, I will show the motivation at TI for investigating and evaluating SLT systems. I'll then proceed with the description of the system-level test. I'll then proceed with the description of the system-level test vision at TI, the SLT system requirements and survey results on several vendors, how they didn't meet our TI requirements. Then I'll get into evaluation of actual SLT equipment at TI and what the return on investment effects look like. And finally, I'll go over what the current SLT implementation plans are at TI. So let's get into motivation. The main driver for TI investigation of system-level test was really the resource drain caused by resolving customer returns from the recent generation of advanced automotive processor devices. We were able to quickly develop test procedures on our device evaluation models, right, the EVMs, that identified the customer returns as fails. But translation of these EVM procedures into our traditional ATE tests was proven to take a very long time for many of these returns. Compounding the trouble with the long ATE translation time was the issue that many of the returns were only confirmed occurring at cold temps. So I put together the table at the right that shows the total engineering effort needed to fully resolve these customer return issues. And then it was eating up, if you added all those different pieces together, about 25% or a quarter of the engineering resources needed for development of a new processor product, right? So in other words, these returns were a significant burden on our new product development resources. This resource burden plus the overall consequences of customer returns on goodwill, you know, really they were the main drivers to begin the SLT investigation. We therefore began our formal investigation of system-level tests as a means to significantly reduce the customer returns and their associated resolution cycle time. So our vision of the SLT machine was to use that same device evaluation module as the core of the test hardware, because we already have proven its capability to adapt and identify customer returns quickly. and remember, these returns weren't easily identified using our traditional ATE methods and equipment. However, when we did this, we found that these EVM test times were quite lengthy. 10, 15 minutes weren't unheard of. We knew we had to parallel test as many devices as possible if we were to use system level tests in production. So this led to us to decide on miniaturizing these EVMs so we can put as many of those as possible on a board, automate the DUT load and unload, get into a single insertion operation where even though we had multiple temperatures that we wanted to test these parts at, we only really wanted one insertion to keep the cost low. And we decided we needed a dedicated controller function for each EVM, put all these together as system requirements. We added the dedicated controller function to enable asynchronous site testing. Just because these tests are so long, we didn't want to have to wait if there was a fail for the full test time to finish. So the graphic shows full-size EVM on the bottom of the slide, right down here, that we're using, and how in the upper portion of the graphic we decided to try to place 8 of these miniaturized EVM versions onto a motherboard to increase our parallelism. In this case, that target EVM size reduction was about 50%, so pretty significant. The number of parallel sites planned for the motherboard, however, was somewhat vendor dependent. We saw the multiple sites range from 4 per board to more than 20. Since the miniaturization was a task that we at TI had to make, the number of systems we wanted to evaluate it needed to be quite limited, right? We had to choose our evaluation folks wisely. So what we did is we took that basic definition and put together some system requirements. Here you can see what these look like. The list of parameters on the left are mainly aimed at the handling requirements of the envisioned SLT system. Some of the more notable requirements there in that list, of course, are the die temp range. We needed to go from cold to hot. At the same time, our DUT power was ranging from 2 watts to 50 watts within the same family and sometimes within the same device. The initial target test time for one insertion was 300 seconds, right? 5 minutes. We wanted to get some proven throughput models to improve our cost of test modeling. And we're looking for a typical target volume of about 1 million units per month. So that kind of shows what the basic system requirements are. On the right, we wanted the vendor of the SLT equipment to supply the EVM controller. So listed on the right are the different EVM interfaces. We were able to significantly reduce the controller interface need in the end to only those needed to start and stop testing, communicate results, and reprogram the EVM firmware as the test procedures change, right? So those are our requirements. We then went and surveyed many SLT vendors. And we broke that survey into those survey results into several categories such as capacity, maintenance, capability, thermal performance, and cost, right? And you can see here that none of these vendors really had checked off all of our boxes in this stoplight chart. But the vendor A folks came closest to meeting all of our needs. So we went ahead and engaged with that vendor to produce a single motherboard system, a pilot system, to proceed with our proof of concept. I might also note that this vendor D is really one of many vendors that really only had Candler only offerings, not supplying the controller function. So this vendor here is our lowest cost version of that list of people just supplying handlers. So we purchased that single board system from vendor A and created an evaluation matrix, which was agreed upon both by the vendor and TI. The first section up here, the CFE, that's the current customer furnished items, included, in this case, 20 miniaturized EVMs. So we had to design up the miniaturized EVM to supply those to the vendor along with the motherboard. Of course, our EVM firmware needed to be developed with the program embedded in there. We had to purchase the EVM sockets, and most importantly, for this evaluation, we supplied both good and bad, meaning devices that were customer returns. The remaining sections are right, like safety and test prep and these miscellaneous items, test execution, so on. Those remaining sections relate to the vendor performance or the system performance. The results of all this evaluation was that the equipment met most of our requirements, and most importantly, it identified all the good and bad devices under test correctly. And we did that using a multi-site configuration in a multi-temp single insertion. So we pretty much were able to prove out our concept. That red fail there on the test execution relates to a minor miss on the temperature transition time requirement that we had placed on the system. The DUT performance came out perfectly, flawlessly. The yellow, of course, relates to a safety issue that we were only able to identify once the system was on site at TI. So that's why there's a yellow. The vendor eventually did resolve that safety issue. So our machine is fully capable of testing out parts right at this time. So again, repeating on these results, the system was able to correctly identify all the customer returns as failing the system level testing. So pretty good news. However, when we look more closely, we saw that there was issue with the solution only was able to test out the temperature range that would capture the customer returns and not the full temperature range of the device spec. So our group needs to consider all the possible future issues when we're developing a new piece of test hardware. So this was a significant gap to us that we needed to close. So what we did is we went back to our survey and picked the next vendor in line and engaged with them to see if they could close those gaps. Right, that vendor was vendor E in that survey list. There was and you know, adding this into our evaluation was no small task, because again, we had to create yet another miniaturized EVM design and motherboard design and put that all together. In the end, we were able to get this get the performance tested, and this graph is a result of that performance testing, showing that vendor E was able to correctly move from the full temp range of the device. It had the right, it met the transition times of the temperature, as well as it took into account the quick and abrupt power changes on the device. All right, so our vendor A gaps were able to be filled by vendor E. So we felt we were at a point where we could go to our senior management and begin talks on how we would go and make this into a full up production system and turn up the crank on the parallelism and automation.
Let me quickly interrupt on the last slide. You mentioned that this thermal behavior you found out fairly late, and you had to do some significant redesign of your modules. Looking back now, would you have done something differently, knowing what you know today, to avoid this redesign and the effort?
Yeah. We at the time that we were doing the initial survey, we did choose the best capable vendor in our estimation. We should have gone ahead and included the device specification in our requirements for the temperature range, rather than just aim at testing out those customer returns. Yeah, I agree that we could have done a better job on defining our requirements up front. Does that answer your question, Mark?
Yep, thank you.
Okay. So as I said, given we've now demonstrated both the multi-site single insertion, multi-temp system level test feasibility, as well as capability to meet the full temp spec range of the target devices for future needs, it was time to consider the costs moving forward of implementing massive parallelism and automation for the various SLT systems. This, of course, drives the need to understand and determine our total insertion costs for the target production volumes. So this graph here shows a cost comparison of two of the systems at various test times and OEE values. These two systems were on the extremes of the capital costs according to the equipment survey. However, you can see that once you this insertion cost from production tells a different story once the actual throughput for the specific configuration is included in the calculations. Right, just exactly how many EVMs we can fit on that system, and if we had to pay for the design development and repairability of the controllers that go along with our EBMs and so on. These values ended up being on the right track to meet our customer return resolution goals. But it started to become crystal clear as we met with some of our senior management that the very high capital cost of the SLT equipment was setting up significant reluctance to accept any production cost of test increases when adding the SLT insertion to the test flow, right? These are very expensive, very large machines requiring a very significant capital investment. So our return on investment was proven, right? We met the initial goal of reducing our burden on our resources for the customer returns, but we determined that the implementation cost burden was too high. So not willing to give up on this concept, we're working well in identifying these customer returns. A compromise of sorts was reached such that the SLT production implementation could move forward if the so-called cost neutrality could be proven between the existing ATE total production test costs and the new cost with the inclusion of an SLT operation. The interpretation of this compromise is that there must be replacement of traditional ATE tests with new SLT testing. This can be accomplished in numerous ways, we believe, such as eliminating one of these traditional test operations entirely and inserting the SLT test, or as we show in the graphic, by eliminating portions of room, high temp, and cold temp test operations and replace them in that single room, high, cold temp system level test operation, right? We had this new capability for multi-temp in a single insertion. We'll try to use that to also reduce the total cost of test with system level test compared to the test without. Unfortunately, however, thus far, after over a year of effort, right, we have not been able to forecast achieving the cost neutrality goal on the target devices. So today, we're still keeping our production system level test plans on hold until we can achieve that cost neutrality. So that result is forcing us to continue with our traditional ATE approach for customer return resolution. And of course, all that implies with the customer. So what's the conclusion of this? What did we get out of all this work, these multi-years and perhaps millions of dollars worth of costs? What we conclude from this system level test integration, investigation, and evaluation work is that this very large capital cost of the SLT equipment is really strongly hindering implementation of production system level tests for these advanced processors at TI. We've even gone so far as to looking into reusing obsolete testers for portions of the system level test hardware to further reduce costs. That was a nice idea, but we found that the the hybrid solution became unacceptable to the space and power needs of that old obsolete equipment. It's obsolete for a reason, right? They're big and bulky and power hungry. And at the same time, repairs on that obsolete equipment becomes difficult when the components internal to the machines are obsolete as well. On the flip side, as we're doing all this work with those automotive processors, we're finding more and more need for system level test inside TI. Examples of some of those needs come from areas such as drift testing for the high-end voltage reference devices and orientation strength testing of magnetic devices, right? You could include opto devices in there as well, and high voltage devices and isolation devices. But the main point behind all of them is that all those devices have even lower tolerance for test cost additions than those automotive advanced processing devices. So until there is some type of cost breakthrough on the system level test equipment or processes using those equipment, at least at TI, we are continuing to employ tremendous engineering resources on finding traditional ATE test solutions rather than implementing 100% production system level tests. Now, having said that, if you know or have an ideas on cost breakthroughs for this SLT equipment or processing, give me a shout, send me some information. I think we should take that as a challenge to the SLT vendors that we need something more than what's available today. So this concludes my presentation. Thanks for your time and listening. Are there any questions?
Rich, thank you very much. Great presentation. So I think you have looked into ways of bringing down cost, and I assume you have looked into combination of SLT with burn-in and maybe the idea of making it more universal to different families of devices, but I guess this all kind of failed. Is that a correct assumption? Or?
That's a correct assumption in that of course, at TI, our goal is always to get out of production level burn-in, right? It would be a nice fix if we were doing 100% burn-in forever to marry up the system level test needs with production burn-in needs. But that's not our strategy today inside TI. But yeah, that's a great alternative for those devices that do have 100% production level burn-in.
And you're talking about alternative implementations on ATE. Can you comment a little bit on what that means, what you're thinking about?
Well, some of those, as I described a little bit, some of it is trying to use older obsolete equipment. Other items there are using different test techniques at the ATE insertion to mimic what happens inside the system level test, right? This presentation explores all the ways we try to move ATE testing onto system level test. But the reverse of that is moving some of the system level test onto the ATE. An example might be for the isolation type devices where we have ISO standards testing requirements, and we'll move those onto the ATE using specific structures on the low boards. That'd be one example.
Okay, and maybe one quick last question. Is the test insertion still a requirement at code test, for example, minus 40 degree?
Yes. Yeah, the minus 40 degree is and cold temp in general is an issue that we're trying to resolve from our side, right? That it does cause a tremendous increase in the cost of the SLT equipment. It's one thing to have thermal heads that can ramp from room temp to high temp, right? That becomes a much easier task than moving the temperature of the die from room temp down to cold temps. And from our survey, it shows that there's even a significant challenge going from like 0C down to minus 40C. And I know our power levels aren't all that great compared to some of the bigger processors, all right? I've seen talk of 300 watt devices and 1,000 watt devices. Those are much more difficult to get to cold temp than ours. But in this case, our customer is automotive, and they set the rules as far as what the temperature range of the part is. And I think everyone who drives a car agrees we want these things to work reliably at cold temp just as much as at other temperatures.
Okay, thank you very much, Rich.
In conclusion, I'd like to very much appreciate our sponsors who've made this event possible and allowed us to do this without registration charge. Our premier sponsor is Kohu. Our emeritus sponsor is JonsTech. Our honored sponsors are ISC, iWin, and TSC. Our distinguished sponsors are Backer Hot Watt, Innovative Circuit Engineering, JMT, Nidec SVTCL, R&D Altanova, and UI Green. Our exhibitors sponsors are ELES, MJC, Phoenix Test Arrays, and Smiths Interconnect. So thank them once again, and when you have an opportunity, please thank them. An extra special thank you to Kohu, our premier sponsor, the market leader in test interface solutions for the most challenging applications. Our honored sponsor, ISC, global #1 total test solution provider. And iWin, the test probes provider for high signal integrity at extremely high speed test. And once again, I would thank all of you for attending and participating in this week. Look forward to seeing you all online the week of October 25th for TestConX China, and then March 3rd through 9, 2022 for our in-person event in Mesa, Arizona. So I wish everybody a good rest of your day. Thank you for your participation.